Solving systems of equations by elimination, also known as linear combinations. In this example, we're asked to solve the system by elimination, and what we notice is both equations are written in standard form. We also notice that the coefficients of the x terms are additive inverses. That is, if I were to add them, the x terms would cancel out or eliminate. So we would get 8y equals 16, and we can solve for y by dividing by 8. So now I have the y coordinate of my solution. To get the x coordinate of my solution, I can use either of the two given equations, substitute 2 for y, and solve for x. Subtract 4 from both sides and divide by 5. My solution is 1, 2. And I have solved this system of equations using a strategy known as elimination. In the second example, the equations are given in standard form. I have the x's above each other, the y's above each other, and the constants above each other. Now some people choose to subtract to eliminate the y's. And what I like to do is I like to use addition. I feel like there's fewer errors that are made, but I want to multiply that bottom equation by -1 to change the sign of the y's. Now when I add, the y terms will cancel out, they will eliminate, and my x terms will be 5x equals -10, so x equals -2. Now I can substitute that value for x into either equation. I'll choose the bottom one. So 2 times -2 plus 3y equals 5. Now I simplify this equation and solve for y. Y equals -3. So the solution to this system of equations is -2, 3. And notice, in this case, both equations were in standard form. I decided to eliminate my y's. I multiplied my bottom equation, all three terms of my bottom equation, by -1. Let's look at the next example. Here I have one of the two equations is in standard form, but the top equation is not, so I'm going to need to rewrite it and subtract 8x from both sides. Now I can see that my coefficients for my x's are not the same, and the coefficients for y's are not the same. But if I multiply that bottom equation by 2, my x coefficient would be 8. So -8x would eliminate with 8x if I were to add them together. So that's what I'm going to do. I'm going to multiply the bottom equation by 2 and rewrite my system. Always a good idea to rewrite the system of equations. Now we can add them, and you can see that the x terms will eliminate, and we get -1y equals -6, so y equals 6. I can substitute that value for y into either of the two given equations. I'll choose the bottom equation. So 4x minus 3 times 6 equals -2. And I will solve for x here. Add 18 to both sides, divide by 4. I get x equals 4. My solution now to this system of equations is 4, 6. So if I were to substitute x equals 4 and y equals 6 into either of the two given equations, I would get a true statement. That's how I could check my solution. Okay, here we have an example where both equations are in standard form. However, there's not one number I can multiply either equation by that will allow me to eliminate one of the variables. So I'm looking at my x terms right now, and I'm thinking about a multiple of 4 and 6, a common multiple, and I'm thinking of the number 12. So if I multiply the top equation by 3, I'd get 12x. Do you see that? If I multiply the bottom equation by negative 2, I'd get negative 12x. And that way my x terms would eliminate. So once again, rewrite both equations. Now I can add these together and the x terms will cancel. And I get negative 19y equals 95. I can divide by negative 19 and get y equals negative 5. Once again, you can use either equation to substitute that y value into. I'll choose the top equation. So 4x minus 3 times negative 5 equals 15. 4x plus 15 equals 15. 4x equals 0, so x equals 0. So my solution is 0, negative 5. So this is a little bit more challenging. Sometimes you'll get examples like this, and you have to consider, do I want to eliminate my x term or my y? And what do I need to multiply both equations by so that that variable will eliminate? All right, finally, a word problem. Carlos has 32 buffalo nickels, some with dates and some without dates. Buffalo nickels without dates are worth 15 cents. And dated buffalo nickels are worth 75 cents, so they're worth more. If Carlos's collection of buffalo nickels is worth $10.80, how many of the coins have dates on them? So we always want to set up our system of equations by establishing what do you want to call x and what do you want to call y. And my convention is, because the dates came first, it says some with dates and some without, I say let x equal dated nickels, y equal non-dated nickels. And because he has 32 buffalo nickels, I can write an equation, x plus y equals 32. And the dated nickels, the 75 cents times x plus 15 cents times y equals a total of 10.80. Now, I'd like to clear those decimals in the second equation by multiplying all three terms by 100 and rewrite my system of equations. And if I multiply my top equation by negative 15, can you see we would eliminate the y's? So that's going to be our strategy. Let's multiply the top equation by negative 15. And now when we add these equations, the y terms will cancel out. We get 60x equals 600, x equals 10. So 10 stands for the dated nickels. I could actually stop right here because the question that has been asked has been answered, 10 dated nickels. But if I wanted to find out how many non-dated nickels, I would use the fact that he had 32 coins, so he must have 22 non-dated nickels, and his solution could look like this. So that is going to be my approach when I have a word problem involving a system of equations. Now let's get some practice. I'll put 2 practice problems out here for you. And it says solve each system by elimination. So example A, I think, corresponds to the first example we did in this video, and example B corresponds to the second.